In section 2.2, we'll be talking about isomorphisms of vector space. So our goal is to define an isomorphism between two vector spaces and use kernels and image to prove that a linear transformation is an isomorphism. All right, so let's start by defining what kernels and images are. So 2.2.1, kernel and image of linear transformations. All right, so let V and W be vector spaces and let T be a linear transformation. The kernel of T is the following subset of V. So it's going to be the set of all elements of V that are sent to the 0 of W by T. And so another way of writing this is to say it's the preimage of 0. Right? The image or the range of T is the following subset of W. It's going to be every image of things that are in V. Okay, so you apply T to all of V. So here's how we'll write it sometimes. All right, so let's start with an example. We talked about how projections were linear maps, so let's apply it to a projection. So example 2.2.1. Let's take V to be the vector 1, 1, 0 and consider the linear transformation. T from E3 to E3, W to projection onto V of W. All right, so I want to find the kernel. That means I need to find all the elements of E3 that the projection sends to 0. So let's take a random element of E3, and I'm going to look at what T does to it. It's going to be the projection onto V of W. That means it's going to be V dot W over length of V squared times W. All right, so V is 1, 1, 0. So when I take the dot product, I get x plus y. The length of V is root of 2, so 2. And then, this is V. Times 1, 1, 0. All right, so we want this to be the 0 vector. And so our only chance is that x plus y is 0. All right, so the kernel of T is the set of all vectors W, so that x plus y is 0. Or said differently, it's going to be the set of all W, so that this dot product is 0. Well, that means W is perpendicular to V. All right, let's find the image of V. All right, so I want to take T of every V, so I want to take T of any X, Y, Z. All right, so that's going to give me, we've already found it, X plus Y divided by 2 times 1, 1, 0. All right, so notice that this can be written as any constant, as some constant, times 1, 1, 0. And so I want to prove that I can get everything that looks like this. All right, so it's clear that this is one of them, but I want to show I can get anything. So I need to come up with one example that hits this. So I'm going to take, I want this to be A, so I'm going to take 2A, 0, 0. That's going to give me A times 1, 1, 0. All right, so this works for any A. And so the image of T is the set of all A, 1, 1, 0 for A in R. And so really it's the span of V. It's the span of 1, 1, 0, and that was our V. And so this is quite nice. The kernel would be everything perpendicular to V, and the image would be everything parallel to V. In fact, let me add a page just to show you what it looks like. So here's V, let's say. And so the image of the projection would be this, and then the kernel would be everything perpendicular to it. And if you think of what projection does, then this makes sense, because everything that's perpendicular is going to be mapped to 0. And then if it's not perpendicular, I'm going to be able to map it on that line.